Welcome back. In this class we're going to talk about aldehydes, specifically the aldehyde functional group and the properties of the aldehyde family of compounds. So what do we need to be able to do in the exam? Well, aldehydes predominantly come up in question 8. They can also appear in question 4, the short questions, but you're usually going to find them in question 8 as part of the larger organic family question. So what do you need to be able to do? Number 1, you need to be able to give a use for aldehydes. Now, whether you can give it a use for formaldehyde, which is methanal, or benzaldehyde, it doesn't matter. Just be able to give a use for an aldehyde. Number 2, you have to be able to apply the UPAC naming system. So it's exactly the same as when we named alkanes, alkenes, and alcohols, but now you are just changing the ending to take into account the aldehyde family group. Number 3, you have to be able to circle the functional group. So identify the functional group and circle it on a diagram. Number 4, you need to be able to compare the boiling points. Now this could be comparing the boiling point between the aldehyde and the corresponding alcohol, or as the chain length of the aldehyde increases, why does the boiling point increase? Spoiler alert, what we learned in relation to alcohols is applicable here. It's the same answer. Next. Number 5, you have to be able to explain the solubility of aldehydes. Is it polar? Is it non-polar? Can it form hydrogen bonds with water? But then you also have to take into account the chain length. So remember, as the chain length increases, the non-polar section gets bigger, and that's going to counteract the solubility provided by the polar part. So see how the same language can be applied to multiple different families? Number 6, we have to be able to draw and name an aromatic aldehyde. Now, aromaticity or aromatic means it has a benzene ring. Now, so starting off with aldehydes, let's go through some of the general key information for the exam. Aldehydes have the functional group where you have a C double bond O, a carbonyl group, and the carbonyl carbon is attached to a hydrogen like that. Now, what else that carbon is attached to, we don't care. It could be hydrogen, it could be another carbon, it doesn't matter. So if I was to draw it like this, the aldehyde functional group is this bit here. And when we write the formula of aldehydes, if I was to write the formula of this, the molecular formula, it would be CH3CHO. So when the formula is written, if you see it written as CHO, that actually is an aldehyde. Now, a lot of people get confused with an alcohol here. An alcohol would be COH or CH2OH, whereas an aldehyde is CHO. Now, with more practice and the more of the practice questions that you do, it will get easier to recognize what functional group is given in the molecular formula. But if you see CHO, straight away aldehyde. Now, aldehydes, when you're naming them, they end in AL. So aldehyde ends in AL. If I was naming this compound on the right-hand side, you follow the longest part of the chain along. There are 2 carbon atoms, so it's going to be ethan for the 2 carbons. Now, for the family, we look for the functional group or the family group. And the family group is an aldehyde. So I'm going to circle the aldehyde part, which is this bit here. And because it's an aldehyde, it ends in AL. Now, we need to have a conversation here because when you are writing the name of an aldehyde versus the name of an alcohol, your handwriting is very important here. If you've ever been given out to for messy handwriting or somebody can't read your handwriting, it's really important that you spell the name of your compound in block capitals. Because I've had students in the past write something like this, where they're not really sure what the aldehyde ends in. So they give me something like this, where it looks like a combination of an A and an O. Now, as an examiner, I have to apply my best judgment here on whether or not to give the marks. And we tend to be a little bit on the harsher side here. So if it's not clear which one you are naming, we can't give you marks. So either take care with your handwriting or spell it out in block capitals and you'll be grand. But if it's ambiguous and it's somewhere between an alcohol and an aldehyde, no, we're not going to give you marks for that. Okay, so other interesting things about aldehydes. So, methanal. Methanal is an aldehyde that has one carbon atom. So you have your C double bond O, and we draw in the aldehyde. Now, because it's methane, there's no other carbons. So the other thing that that carbon is attached to is a hydrogen. Now, the commercial name of this compound is formaldehyde, and it's used in embalming and preserving biological specimen. If you've ever been in the Natural History Museum and you see stuff floating in the jars of liquids preserved, that's what the liquid is. It's formaldehyde. Now, with aldehydes, they're always going to end in Al, and they will always be at the end of the molecule. They can't be in the middle, and it's actually due to what the carbonyl carbon is attached to. So if we look at the carbonyl functional group over here on the left-hand side in ethanal, the fact that the carbonyl carbon is attached to a hydrogen, hydrogen can only form one bond. It can't form another bond. So your aldehyde has to be at the end of the molecule. Now, when it comes to naming this compound, you don't need to worry about the numbers. So with the UPAC naming, you don't need to include numbers because the aldehyde will always be on carbon 1. Because it's at the end. Okay, so if I was to produce a bigger aldehyde, such as, so if I get rid of ethanal and I extend the chain like this, this molecule, you have 4 carbons in the longest straight part of that chain, so it's butane. The family, it's an aldehyde because of this bit here. So it's butane-al. Now, again, you don't have to say butane-1-al. It's not necessary because the aldehyde is the functional group and that's always going to be carbon number 1. Okay. Now, other things of note for aldehydes. Now, it's important that we can talk about the aromatic aldehyde. Now, this does come up quite a bit on the exam. Aromatic in chemistry, in organic chemistry, means benzene. So an aromatic ring is a benzene ring. Now, there's only one aromatic aldehyde that you have to be able to draw. It's called benzaldehyde. Now, to draw it, you draw a benzene ring. You can draw it as 3 doubles and 3 singles, or you can draw it with the circle. It doesn't matter. It means the same thing. And then sticking off the side of it, you draw one aldehyde group, like that. And it doesn't matter which carbon on the benzene ring you pick because they are all the same. So that is benzaldehyde. Now, why you need to know that is one of the mandatory experiments is the synthesis of benzoic acid. And benzaldehyde is one of the intermediates that's formed on the way to forming benzoic acid. And benzaldehyde has a very distinctive smell, and you need to know this. It smells like almonds. Now, how that could be asked on the exam is, draw the structure of benzaldehyde, 3 marks. Or it could ask you, name the compound that is responsible for the almond smell in the formation of benzoic acid. So it's benzaldehyde. And then you should be able to draw it as well. Now, properties of aldehydes. Okay. For the properties of our aldehydes, they are polar. So aldehydes are polar covalent. And the reason why they are polar is because of the carbonyl group. The carbonyl group in chemistry is a polar group. Your carbon has an electronegativity value of 2.55, whereas the oxygen is 3.44. The electronegativity difference between carbon and oxygen is big enough for that to be a polar covalent bond. Now, if you're not sure why, so go back to your bonding topic. If your electronegativity difference is bigger than 1.7, then you have an ionic bond. If it's between 0.4 and 1.7, then you have a polar covalent bond. And if it is less than 0.4, then you have a non-polar covalent bond. And for something to be polar covalent, it has permanent delta plus and delta minus dipoles on the molecule. So if I was labeling which one is the delta plus and which is the delta minus, the oxygen is always delta minus and the carbon is delta plus. And the reason for that is oxygen is more electronegative. The number for oxygen's electronegativity is bigger than the number for the carbon. So it has the bigger electron pulling ability. Now, aldehydes have a carbonyl group, so they are going to be polar. If I was to draw a couple of famous aldehydes here, so we already drew methanal. If we draw the next one, which is ethanal, because you have two carbons, or propanal. Okay, so they all have the aldehyde functional group, and the aldehyde functional group is a polar group, where we have the delta minus on the oxygen, delta plus on the carbon, and they're all polar, like that. Now, one thing I'm going to get asked here is if any of you have watched the bonding videos very carefully. I said there are 3 shapes that even if you have polar covalent bonds, the molecule is non-polar, and one of them was trigonal planar. So we would have looked at molecules like BF3, which have huge electronegativity differences. Boron is the central atom, bonded to 3 fluorines. Then your fluorine is delta minus and your boron is delta plus. But even though you have polar bonds, the molecule is non-polar. Now, that is the case for BF3. Now, if I move BF3 over here, compare it to the molecule of methanal above it. Now, even though the carbon in methanal on the left-hand side is a trigonal planar carbon, it's different to the BF3 because in BF3, all of the atoms attached to the boron are the same. In methanal, I have an oxygen up there and I have hydrogens here. So in this case, your dipole moments are not going to cancel because you don't have the same amount of force pulling your electrons in 3 equal directions. So your dipole moments don't cancel. So even though that is technically a trigonal planar structure, this idea of the molecule being nonpolar does not apply here. Earlier on when we talked about symmetry, we only really talked about it where you have a central atom bonded to 3 of the same atom. But this case, the carbon is not bonded to 3 of the same atom, 3 atoms of the same element. Okay, so all aldehydes are polar covalent. Fantastic. Now, if I was to look at what intermolecular force aldehydes have with other aldehyde molecules. So we know it's polar. Now, normally, when something is polar covalent and you're trying to figure out what the intermolecular force is, it's a 50-50 shot of picking the right one, so it's either going to be hydrogen bonding or dipole-dipole. So, ask yourself, does methanal, we'll go with methanal first, have an oxygen, nitrogen, or fluorine? Yes, there's an oxygen. Now look carefully at that oxygen. Is there a hydrogen attached to that oxygen? No. So it can't have hydrogen bonding between molecules. Instead, it has dipole-dipole. So if I draw another molecule of methanal here, and I label my dipoles the way they were originally, where we have delta minus, delta plus, delta minus, delta plus, and then you have delta plus to delta minus intermolecular force between permanent dipoles. That is a dipole-dipole intermolecular force. So aldehydes, because they have dipole-dipole forces, they will have higher boiling points than corresponding alkanes. When I say a corresponding alkane, I mean an alkane with the same number of carbons. So in this case, I've got methanal, so it would have a higher boiling point than the corresponding alkane, which would be methane. But if I was to compare it to methanol, the alcohol, alcohols have hydrogen bonding. So that is a stronger intermolecular force, so methanol would have a higher boiling point than the aldehyde. So if I'm comparing alkanes, they will have the lowest boiling point. Then you have aldehydes in the middle. And then you have alcohols because of their difference in intermolecular forces. Your alkane only has van der Waals. Aldehydes will have dipole-dipole and hydrogen bonding in the alcohol. Okay? Now, you have to be able to look at molecules and pick out which of them has the higher or lowest boiling point and explain why. So it's the same type of answer we've been using before. State whether it's polar or non-polar, then identify what the intermolecular force is, then you compare the strength, then you link to the energy needed to overcome that intermolecular force. Now, so that's our boiling point. Let's talk about solubility in water. Well, aldehydes are polar covalent, so the short chain aldehydes, they are absolutely soluble in water. So again, same as the alcohols, up to about C4 will be soluble in water. Round about C4 tends to be when it's soluble. However, if you go above 4 carbon atoms, then the solubility in water dramatically decreases. So if I asked you, is methanal soluble in water? The answer is yes, it is. Now, if you're asked to draw a diagram showing that it would be soluble in water, you draw out the aldehyde, you put in the delta minus and the delta plus dipole, then you label water, or you draw in water with delta minus and delta plus. You have a negative to positive attraction like that. Now, this is going to drive you nuts. When you have aldehydes in water, that intermolecular force that's forming between the aldehyde and the water is called a hydrogen bond. When your aldehyde is forming an intermolecular force with another aldehyde, it's dipole-dipole. However, the aldehyde can hydrogen bond with water, because a hydrogen bond is a type of dipole-dipole intermolecular force. It's just a stronger type of dipole-dipole force. Now, why it's that? So if I get rid of my dipoles, just to kind of make my diagram a little bit less messy. Okay? Right. You have a delta minus to delta plus force of attraction between my two molecules, between the water and the aldehyde. Now, we know it's dipole-dipole, a type of dipole-dipole, but we need to be able to label it properly as dipole-dipole or hydrogen bonding. So the normal sequence of events is you ask yourself, does it have oxygen, nitrogen, or fluorine? If we look at the aldehyde, there's an oxygen there. Does that oxygen have a hydrogen attached? No. But if you look at the water has an oxygen. Is there a hydrogen attached to that oxygen? Yes. So the hydrogen bonding component is actually coming from the water part of the interaction. And all it is a delta plus to delta minus force of attraction, where on one of the molecules you have an oxygen, nitrogen, or fluorine attached to a hydrogen. So that is a hydrogen bond. Now, this is where students get confused. Aldehydes form dipole-dipole forces with other aldehydes, but they can hydrogen bond with water. So if it asks you, is methanal soluble in water? Your answer will look like this. Yes, it is soluble. Why? So then we spell out methanal is polar. Water is polar. And no being lazy here, you have to spell it all out. Methanal can form hydrogen bonds with water, and that's actually why it is soluble in water. Okay. So the short chain aldehydes up as far as about C4, they will be soluble in water, but the longer chain ones are not. Now we're going to come at this in the same way that we did the alcohols in the previous topic. Okay. Long chain aldehydes are not soluble in water, even though they have a polar group. So now if I was to draw a long chain aldehyde, 1, 2, 3, 4, 5. This molecule is called pentanal because it has 5 carbons in a long straight chain. Now the polar part of this molecule is where you have the delta minus on the oxygen, the delta plus on the carbon. So this part of the molecule over here is polar covalent. Technically it's just the carbon oxygen, the carbon hydrogen is not. Then this bit here on the left hand side, all of this bit here is non-polar covalent. So as the chain length increases, the non-polar part gets bigger, and that counteracts the solubility provided by the polar part. Exact same word for word answer as what we learnt off in the alcohols. Just be careful here that you don't call it a polar OH group, because it's not a polar OH group. That was alcohols. This is the polar C double bond O group. Okay? Now, let's have a look at a couple of worked examples. Now, these worked examples are done out in the notes. I'm just going to make that a little bit smaller so it's not cut off. Okay, worked example number 1. The boiling points for ethane, ethanol, and ethanal are shown below. Account for the differences in boiling points for all 3 substances. Now, I'm going to highlight the ending to each of those names. I have ethane, ethanal or ethanal, and ethanol. They are 3 different families of compounds. Now, if I was to draw them all out, just to kind of make my life a little bit easier, it's not essential here, but if you're struggling to figure out whether something is polar or not, a diagram can actually help you. That's ethane. Ethanal is the aldehyde, so Al is the aldehyde. And then ethanol, you have your alcohol group, which is the OH. Like that. Now, when you are comparing boiling points, there's 4 steps that you have to go through. Number 1, you state whether the compound is polar or non-polar. Then, based on whether it's polar or non-polar, number 2, you identify what the intermolecular force is. Number 3, you compare the strength of the intermolecular forces. And number 4, you talk about the energy needed to overcome them. So I'm going to flick over to the right-hand side. And it asked me to account for the differences. So I just need to explain why they are different. So I have ethane, ethanal, excuse me, and ethanol. Now, ethane, it's an aldehyde, so that is non-polar covalent. If something is non-polar covalent, the only intermolecular force it can have are weak van der Waals. Perfect. Then we move on to ethanal. Now, ethanal, we've already said, is polar covalent. The polar part is the carbonyl group, where you've got delta minus and delta plus. So with ethanal, we know it's polar covalent. Now with polar covalent, you have a 50-50 shot of picking the right one. We need to write down either dipole-dipole or hydrogen bonding. Go for hydrogen bonding first. It's the easier of the 2 to eliminate. Looking at the structure of ethanal, does it have oxygen, nitrogen, or fluorine? It has an oxygen. Is there a hydrogen attached to that oxygen? No. Therefore, it's dipole-dipole. So we have dipole-dipole intermolecular forces. Now we need to do the same for ethanol, the alcohol. Now ethanol has an OH group over here. Same as in water, it's the same type of a group. Water is not an alcohol, by the way, because it doesn't have carbons. But you've got delta minus and delta plus. If you're not sure about that, work it out based on your electronegativity differences. So ethanol is polar covalent. Right, dipole-dipole or hydrogen bonding. Go for hydrogen bonding first. Is there an oxygen, nitrogen, or fluorine? Yes, there's an oxygen. Is there a hydrogen attached to that oxygen? Yes. Therefore, alcohols have hydrogen bonding intermolecular forces. Perfect. Now you've done step 1 and step 2 for each of the 3 compounds. Our next step is to comment on the strengths. So van der Waals are the weakest intermolecular force. They don't need a lot of energy to overcome. Now don't use the word break. Next up, we have ethanal, so dipole-dipole. Dipole-dipole forces are stronger than van der Waals. But they are weaker than hydrogen bonding. Again, intermolecular forces. Therefore, more energy is needed to overcome dipole-dipole forces than van der Waals. Now I'm abbreviating just because I'm writing the same thing out. So just in the exam, you are not allowed to abbreviate. I'm doing it just so that it's a little bit shorter. So more energy is needed to overcome dipole forces than van der Waals. Therefore, ethanal has a higher boiling point. Than ethane. Now remember to spell out boiling point. Don't be lazy because BP could also stand for bond pairs depending on the abbreviation, so spell it out. Then hydrogen bonding is the strongest intermolecular force, so requires the most energy to overcome. Therefore, ethanol has the highest boiling point. Now that's going to look like overkill. And it technically is. But I don't care. That is what the examiner is looking for. State the intermolecular force, compare the strength, and link it to the energy needed to overcome it, and you're going to get full marks. You'll also be surprised once you start doing the exam questions how easily boiling point questions are marked. But we want to be writing our answer in the perfect layout so that when you sit down in the exam and you're answering a boiling point question, your format is the same every single time. It doesn't matter whether you're dealing with alcohols or aldehydes or whatever else, that you're hitting the same format. So on autopilot, you can write out your full answer. And remember to kind of ram it home to the examiner that you understand we're talking about intermolecular forces, forces of attraction between separate molecules. And don't mention anything to do with breaking bonds because you'll lose marks for that. Now, our next worked example, let's have a look at worked example number 2. So this one. Draw a diagram showing the permanent dipole-dipole interactions between molecules of ethanal. This is very similar to an exam question that came up a couple of years ago, and students could not answer this properly. So for this, we need to draw molecules of ethanal. So I'm going to draw out ethanal. There's one. And I need another molecule of ethanal, like that. Next, we label our delta plus and delta minus on the oxygen, delta plus on the carbon, on both molecules. And then you have a delta plus to delta minus force of attraction, and then we have to label it as dipole-dipole. Like that. And there is your 6 marks. Now, to get those 6 marks, number 1, I need to see the dipoles, the delta plus and delta minus. And the next thing I need to see is the dotted line joining the delta plus on one to the delta minus on the other. Now, in your notes, to save space, because it is quite a large molecule to draw, I actually drew them on their sides, which is fine. So if you prefer to draw them sideways, so in your notes, I drew them like this. Both of these molecules are still ethanal. And then you have your delta plus to delta minus, and that is your dipole-dipole force of attraction between 2 separate ethanal molecules. Next, let's look at worked example number 3 from your notes. Predict whether ethanal is soluble in water and draw a diagram to support your answer. Now, this one in particular, this came up about 3-4 years ago, and it was not answered well. Not at all. But students overthought it. Instead of just showing a diagram, loads of people tried to explain in words what they were talking about. But a load of students fell into a trap because they kept talking about bonds in a molecule. No. It's intermolecular forces that explain solubility and boiling points. So, predict whether it is soluble in water. Ethanal is a short chain aldehyde, so yes, it is soluble. Now, for just the word yes, you get 3 marks. Now, that's one to watch out for because quite common in the exam when you're asked, is this soluble in water? You need to make a yes or no statement. Now, it's enough to say yes. You don't need to say yes, ethanal is soluble in water. It's enough to say yes. But just remember to include that it is soluble or that it isn't. You have to include the statement and not just the explanation. Draw a diagram to support your answer. So we draw a diagram of ethanal. Like that, and then we include a diagram of water, H2O. Now, make sure you put your dipoles, your delta plus and delta minus partial charges on the molecule because the examiner will be looking for them. And they won't give you marks if they are not included. Then you have a delta plus to delta minus force of attraction between them, and we label it as a hydrogen bond. Now remember, aldehydes form hydrogen bonds with water, but they form dipole-dipole forces with each other. And why it's a hydrogen bond? It comes from the water. In the water, you have an oxygen with a hydrogen attached, so the dipole is bigger, leading to a stronger intermolecular interaction because it's a stronger force of attraction due to the bigger dipole. Then, for that diagram, you're going to get your full 6 marks. Now, what we're looking for there, showing your dipoles is 3, and then your dotted line from delta plus to delta minus, that's the other 3. Worked example number 4. Explain why the solubility of aldehydes decreases as you increase the length of the alkyl chain. So it's the same as the alcohols. As the chain length increases, the solubility decreases. which is what's given in the question, but I'm giving out what I've learnt off before. Now, why that is the case. So what are we giving as our explanation? Because as the chain length increases, the non-polar part of the molecule, the carbon chain part of the molecule, is getting bigger. And because the non-polar part is getting bigger, this counteracts the solubility. The bigger non-polar part counteracts the solubility or overcomes the solubility provided by the polar part, or the polar C double bond O part. Okay. Now, solubility and boiling point, you're going to please expect to see one of those two in question 8 this year. So we need to prep for it. But the fact that we're learning off this answer now for 2 separate functional groups, for alcohols and aldehydes, you can apply it to all of the other families as well. So it's not like we're learning it off for each of the 8 different families. You learn it off once and then you tweak it to apply to each family. Now let's have a look at the practice questions in your notes where you're actually starting to put pen to paper for yourselves. So up first, name each of the following molecules. Now being able to give the UPAC name, it's the UPAC name we're looking for, is worth 3 marks in the exam. So up first, A, you have 3 carbon atoms in the longest straight part of that chain. So its name has to start with propan. Then we look for a family group. The family group here is this bit. You have a carbonyl group and the carbonyl carbon is attached to a hydrogen. So this is your aldehyde. So it will be propan al. Now remember, be careful with your handwriting. Make it very clear that it's Al, not Ol. The next one, we have count the longest number of carbons in the longest straight part of the chain first. We have 4 carbon atoms in the longest straight part of the chain, so it's butan. Then we go looking for the family group. The family group on this molecule is an OH, which remember is an alcohol group. Now we need to count the number of carbons to tell the examiner what number carbon the side group is on. So count from the left, you have 1, 2, 3, 4. Now my alcohol group is on carbon number 2 and it has to end in OL for an alcohol. 3 marks each. The next one. Part C. Count the longest straight part of that chain. You have 5 carbon atoms, so it's pentan. Then we look for a family group. We have a C double bond O, and that carbonyl carbon is attached to a hydrogen. That is an aldehyde, so it's pentan al. And remember, for aldehydes, the aldehyde group is always on carbon 1 at the end of the chain, so you don't need to include numbers. Now this lovely one over here, you have a benzene ring. That's my benzene ring. And then your family group is this bit here, where it's an aldehyde. So put that together. We have benz aldehyde. Three marks each. Now, let's have a look at more difficult questions, but I would recommend that you draw and name the rest of the compounds that are found in your notes, because it's really good practice now that we're starting to build up the different families of compounds that you can differentiate between the different families at this stage. So question number 3. Predict whether methanal or butanal is more soluble in water. Explain your choice. Now remember, this is a chain length question. The shorter chain aldehyde is the more soluble one. So methan is 1 carbon, butan is 4. So my answer is methanal is more soluble. And I get 3 marks for that, so I'm halfway there. Now, why? Now, you can either go after this as it has the shorter chain, or you could say butanal has the longer carbon chain. Has the longer carbon chain, which is non-polar, covalent, whereas methanal has the shorter carbon chain, therefore it's unlikely for the non-polar part to overcome the solubility provided by the polar part. Next. Number 4. Predict whether butanal or butanol has a higher boiling point. Explain your choice. Now, take a second. We have butanal and butanol. So I'm comparing an aldehyde to an alcohol. At this stage, you might find it beneficial to draw out your structure. So butan is 4. But when you get faster at these, you don't need to draw them out. It's just for now, while you're still getting used to them, you might find it beneficial to have a diagram. And we have delta minus, delta plus, that's my butanal, and butanol, I'm doing it as butan1-ol, just to put it on the end to make things nicer. We have delta minus on the oxygen, delta plus on the hydrogen. Now, for explaining their boiling point, so boiling point questions, we're going straight in for intermolecular forces. Now, if I was to look at those two molecules, so butanal, is it polar, is it non-polar? It is polar. Now, 50-50, does it have dipole-dipole or hydrogen bonding? So you ask yourself, does it have oxygen, nitrogen, or fluorine? There's an oxygen. Is there a hydrogen attached to that oxygen? No. So it can't be hydrogen bonding, it's the other one. We have dipole-dipole, intermolecular forces. Perfect. Now we do the same for the alcohol. Is it polar? Is it non-polar? It's polar. Does it have an oxygen, nitrogen, or fluorine? It has an oxygen. Is there a hydrogen attached to that oxygen? Yes. So the alcohol has hydrogen bonding as the intermolecular force. You're halfway there. Which is stronger? I'm going to move over here to the right-hand side. So hydrogen bonding is a stronger intermolecular force than dipole-dipole. And because it is a stronger intermolecular force, more energy is needed to overcome hydrogen bonding. Therefore, make a statement about the boiling point. Oh, that's not ethane. Apologies. Butanol has the higher boiling point. Now, it might look like overkill for that answer. I don't care, because you're going to have to go through those steps anyway in your head. So you might as well put it on the paper where the examiner can give you marks for it. Now, that is pretty much it for the aldehydes. Now, at this stage, I'm just going to take a second because we're starting to build up our different families of compounds quite quickly. So I'm just going to do a summary of all of the different families that we have seen so far. First up is an alkane. Okay. Now, alkanes we saw them in question 6. Alkanes have the general formula CnH2 2N plus 2. When you are naming them, they end in ANE. So the ending is ANE. And how you spot an alkane, they have all carbon-carbon single bonds and only carbon and hydrogen in their molecules. Like that. And that's my alkane. The next one that we came across was an alkene. Alkenes have the general formula CnH2n. Now, alkenes end in ENE. And how you spot them, you have a carbon-carbon double bond between two carbon atoms. Like that. Now, if I was to name these two molecules, the one on the left, 2 carbons, is eth, and it's an alkane, so it ends in ANE. The one on the right, 2 carbon atoms again, but now it ends in ENE because of the carbon-carbon double bond, the alkene. The next one that we came across was an alkyne. Now, alkynes, when you're naming them, will end in YNE. And remember, we don't need to learn the general formula for these because there is only one alkyne on the Leaving Cert course. And an alkyne is where you have a carbon-carbon triple bond. So ethyne is the only one you could be asked. Then, after our hydrocarbons, our next family of compounds that we saw were alcohols. Now, alcohols end in OL. Now, I wouldn't recommend learning off the general formula for alcohols. It's not necessary because you can spot it from the formula. So if I was drawing an alcohol, you have an OH group sticking off of the main carbon chain like that. And this will be ethan for the name, and it ends in OL to indicate that it's an alcohol. And my last one, I'm going to squeeze it in over here on the side, is my aldehyde. Now, aldehydes end in AL. Be careful with the name, be careful with your spelling. So they end in AL. And the aldehyde functional group is where you have a carbonyl group, and the carbonyl carbon is also attached to a hydrogen. Now, the naming of this, you have 2 carbon atoms in the longest straight chain, so it's ethan, but now it's Al for the aldehyde. If I was to write the formula for the alcohol, that alcohol would be CH3, CH2, OH. That aldehyde would be CH3, CHO. Now, from the formula, how you recognize that the alcohol is the alcohol is you have an OH at the end of the chain, like they could be in the middle in brackets either. Whereas the aldehyde, you will see CHO written like that, not COH. It's CHO for the aldehyde. Okay? Right, that is a summary of all of our family groups so far. So we've covered 5 of the 8 that you're going to see. Now, for the next families, if you can name the aldehyde properly, there's no reason why you'll have any problems with ketones, carboxylic acids, etc. So spend a little bit more time getting used to the aldehydes, explaining solubility, explaining boiling points, explaining how as the chain length increases, the solubility decreases. Because when it comes to the next family of compounds, you're going to be applying that same information again. So our next couple of videos are actually going to be a lot shorter than the aldehyde one because it's just repetition of the same information.